Hey folks, this is part one here on our introduction to electricity. I wanted to kind of talk you through this PowerPoint and this topic because it's really important. So I'll be jumping back and forth between here. I actually don't need you to do a crazy amount of this atom stuff, so that's why I wanted you to check this out. Um, Let me jump back to here. Okay, so we're going to skip some of this, although it is important that you know that, and this is the first thing on your guided notes, that electricity is the movement of electrons. It's kind of how it got its name. Invisible force that provides light and heat and sound and motion. So all sorts of crazy stuff, right? So write that part down. It's when it goes all atomic level that we're going to kind of skip some stuff. But okay. So without electricity, you couldn't have any of your cell phones or any of that stuff. So make sure you're writing this down as you go. You know, right there. Light, heat, sound, motion, and all that stuff. Is that focused? Hold on. I'll jump back to here and replug this in. Ooh. Oh, hey, there's me. So anyway, elements. So this is where we're going to kind of skip over because hopefully we're not going to, go too far in because we have enough different things to learn as far as the atomic level and atoms and stuff like that. If you know about electrons and how they go around an atom, so we're going to skip some stuff. We're going to skip this stuff. Just as long as you know that electrons are on the outside of an atom and they can sometimes break free from their atom and go displace other electrons and create charges. So we're going to skip all this good stuff. There's Bohr model. You can read it, and that's cool. But what you got to get out of this is what makes a good insulator and what makes a good conductor. So here it is. If you have something like copper, there's a lot of copper wires in electricity, and there's a reason for that. That's because on their outermost orbit of electrons, there's just a single electron. And it's a great conductor because it will easily give up that one electron to let electricity flow through it. And if it had one or two, especially one, it's great at giving up electrons. So it's a conductor. If it has 8, it's full and it won't do anything. That's like the inert gases. Or here's sulfur that has 6 out of the 8. Is it going to give up all 6 of those? No. It's going to want to accept electrons. So instead of giving up its electrons, which is a conductor, this guy's called an insulator because it likes to receive rather than give off electrons. Okay, so jumping back here, I'm going to show you what you can skip over. Oh, what the heck? Hold on. Please pause. There we go. So on here, we don't have to do this stuff on components of an atom. You don't have to do this stuff on atomic number. We don't have to do this stuff. Okay, so we're kind of skipping some of this stuff. It's good stuff, but it's like past our ability here. Or not our ability, it's just we don't have time for that. So is copper a good conductor or insulator? It's a conductor. Okay. And then how many electrons are in its valence orbit? There's 1. Is sulfur a good insulator or conductor? Insulator. And if we answer that same question, there's 6. So it's a good conductor because it gives up electrons. This one accepts electrons because it's closer to it wants to fill its orbit. The other one wants to give it up to kind of free its orbit. All right, so now back to the important part. What we care about is electricity, which is the electron flow. So jumping back here, So we got to skip some stuff, right? Here we go. Electron flow. The electron from one orbit can knock out the electron from another orbit. So write that down in your guided notes. And when an atom loses an electron, so loses, it seeks another to fill its vacancy. So this is a good animation. This is what the electron flow, and this is what electricity looks like at the... Oh, is it not going to play that? Come on. Shoot. I thought I was going to play it. I might have to be in present mode. I don't know if you'll be able to see that. Shoot. Because it shows... oh, man. Never mind. Didn't work. Gosh darn it. But anyway, I'll show you. If this one gives up and jumps over to here, it'll knock another one out. And that guy will go over here, knock another one out. That guy, one gets knocked out, gets pushed to the next one, and basically makes a flow of electrons. And that's kind of what electricity is. So electricity is created as electrons collide and transfer from atom to atom. So that's what electricity is on the lowest level, which is pretty cool. So conductors have very few electrons in their outer, like silver, gold, copper, aluminum, most metals. Insulators, electron flow doesn't happen much because they have a lot of electrons. So you got your glass, mica, quartz, gases don't send things on. Rubber, you know, is an insulator. All right, so here, kind of the same deal. And you can fill in your guided notes with those things right there. So yeah, if I jump back to my notes here, you'll see conductors easily flow between 1 and 3. If it has 1, it's even better at being a conductor. And if it has 5 through it, it's difficult. 8 kind of doesn't conduct electricity at all. And then there's some in the middle with 4. They're called semiconductors. But now we're getting to the good stuff. This is what we wanted. This is what we came here for, is electricity. So this is the most important. So if your brain wasn't turned on yet, get it working. An electrical circuit is a system of conductors and components forming complete path for a current to travel. So if you think of a circuit, you're thinking of just a path for electricity. So in our notes, we're basically saying path, because that's what a circuit is. And then the properties, these are the 3 big variables we're going to have, and we're going to solve problems with all sorts of things missing. So voltage is measured in volts, and it's symbolized with a capital V. Current is measured in amps, named after a person named Ampere, and it's given an A, as a capital A as its unit. Resistance is measured in ohms, which is like, you know, the noise you make when you're meditating. It's capital omega, which looks kind of like a horseshoe. So make sure you get those in your notes. Those are super important. Those are the 3 categories we're going to solve all our equations in. Okay, so those are very, very important that you know it's volts, amps, and ohms, and the symbols that go with them. Okay, so here's what I like, this analogy of what electricity is: the flow of electric charge measured in amps. When the faucet is off, is there any flow? No. When the faucet is on, is there any flow? Yes. So current you can think of, I like this water and plumbing issue. And you can think of, like, is water flowing? That's your current. So it's measured in amps, amperes, named after I think it was a French guy who did it. So make sure you're getting your notes, you know, up to date with that stuff. It's the flow of electric charge. And then here, when the switch is off, there is no current. When the switch is on, there is current. Okay, so here's something weird in engineering. And that is, oh, we already did that one. Here's what's weird. When people first were discovering, I guess, electricity and investigating it, they thought this is like a battery or a power source. You know, on a battery, either on a car battery, there's a positive end and a negative end, right? So when people first started doing electricity, they assumed that your electricity flowed from positive to negative. Well, later on, when they figured out they're electrons, and electrons have a negative charge, they actually discovered way down the line that electrons actually flow from the negative towards the positive because they are negative charges. So this is called conventional current because it's what people used to think. This is what actually happens. So which one of these things do you think we go with? The thing people used to think that was wrong, or the thing that is right? Well, guess what? We go with the wrong one. We still draw our diagrams as if it flows from positive to negative, even though we know better, which is crazy to me. But anyway, it's been done so long, I think they're like, we don't need to worry about it. But you know what the good news is? It doesn't matter if you draw it this way or this way. The problems still work out the exact same, and your answers still come out the same, and electricity still works the same. So I guess it doesn't care if you don't know exactly what it is. So anyway, take a minute, update your guided notes there. Alright, so hopefully you update your guided notes there and realize that we still use conventional even though we know it's wrong. Okay, so now we talked about amps, and current is the water flowing or not. Voltage is a different thing. It's a little harder for people to understand, but when you think of it this way, think of your battery. Your battery has a voltage whether it's turned on or not. And you think of voltage like the pressure that causes the current to flow. So you have a big tank of water. The pressure that's causing this water to flow out is your voltage. If you have a bigger tank, you have more pressure, you have higher voltage. So measured in volts, this is the second of the big three. So when the faucet is off, is there any voltage? Heck yeah, the pressure is there whether you turn on the faucet or not. When the faucet is on, is there pressure? Yeah. So voltage is the same no matter what. It's going to be there. It's whether or not you turn it on or not. So that's why it says like a 9-volt battery. It's always a 9-volt battery, whether or not you have current. So that's two of our big three. The third one is resistance. So resistance is the opposition to flow. And basically, you want to think of if a rock came down here and got stuck, and there was an animation for this, but I can't make it work right now. It slows down the flow. And that's what resistance is. And you're like, why would I ever want to slow down the flow? And the reason is a lot of your electrical components can only take so much current, or they would fry all the circuits. So you use resistors to kind of control your current. So sometimes you want to throw rocks in there, or think of like rocks in a stream that slow it down. You want to control the flow, and that's what resistance is used for. So jumping back to here, you want to say voltage is the force, and it's there whether or not you turn on your current. It's measured in volts. The battery provides pressure that will push a current through the bulb. Resistance is the opposition to current flow, and it's measured in ohms. Resistors are components that create, here let's jump back and finish this up. So resistors are components that create resistance. That's shocking, right? And if you put a resistor in there, it'll cause the bulb to become more dim. So if I slap something that slowed down the flow, the bulb would go from this bright to more dim if you put a resistor on there. So that's just the intro, and when we come back for the second day, we're going to do a bunch of problems that involve these voltage and amperes and stuff. So hope you got through this part, and we'll continue on later tomorrow.